Hi. Today I want to continue our discussion of descriptive chemistry with a quick look at acid-base reactions. Now, in an acid-base reaction, a hydrogen ion, H+, is transferred from one chemical species, called the acid, to another chemical species, called the base. An example of this is HCl, hydrochloric acid, plus ammonia, reacting to form chloride ion and ammonium ion. And what's happening in this reaction is HCl, which is a molecule, hydrogen chloride, reacts with ammonia. A hydrogen ion is transferred from the HCl to the NH3, and the result is two ions. The HCl has lost H+, leaving it with a negative charge, Cl-, and the NH3 has gained H+, and so it forms the NH4 ion with a positive charge. So in these reactions, an acid is a substance that forms hydrogen ions when it's dissolved in water. There are many examples of acids. One that is common to work with in the laboratory is called nitric acid. When nitric acid is dissolved in water, it forms hydrogen ions and nitrate ions. And this is a typical example of acid behavior. Most acids that you'll encounter are molecular compounds. Nitric acid, HNO3, is a molecule. And when you dissolve it in water, it dissociates into ions. So HNO3 is not an ionic compound, but when you dissolve it in water, it breaks up and forms ions. So it forms the hydrogen ion H+ and the nitrate ion NO3-. Now, nitric acid is an example of something called a strong acid, which means that when it's dissolved in water, all of it dissociates into ions. So 100% of the nitric acid molecules in the water will be dissociated into hydrogen ions and nitrate ions. And this isn't always the case. There are many examples of acids that do not fully dissociate. One of those is carbonic acid, H2CO3. When it's dissolved in water, it does dissociate to form hydrogen ions and bicarbonate ions, HCO3-, but this does not happen completely. Carbonic acid is a weak acid, and so not all of it dissociates to form hydrogen ions and bicarbonate ions. And one way that this is frequently indicated in the chemical reaction is, instead of writing the reaction with a single arrow pointing strictly to the right, we use double arrows pointing to the right and to the left. And this is a way of emphasizing that not all of the reaction goes to form products. You end up with a mixture of intact carbonic acid plus some hydrogen ion and some bicarbonate ion. Okay, now before I continue, I want to say a little bit about notation, about how we describe the chemical species involved in acid-base reactions. And this concerns the hydrogen ion. So naked hydrogen ions don't exist in aqueous solution. Anytime you've got hydrogen ions being formed, they're always stuck to something. When you're talking about aqueous solution, the hydrogen ions are stuck to water. By sticking to water, they form hydronium ions with the formula H3O+. So the idea is that a water molecule, H2O, can pick up an H+, and become H3O with a positive charge. And this is called the hydronium ion. And this is the form that hydrogen ions take when they're dissolved in water. Now, many chemists insist on emphasizing this fact by always writing H3O+ in aqueous solution rather than just writing H+ in aqueous solution. So, for instance, instead of writing HNO3 in aqueous solution dissociates to make H+ aqueous plus NO3- aqueous, a lot of people would insist on instead emphasizing the fact that the hydrogen ion ends up attached to water by instead writing this reaction as HNO3 aqueous plus water gives hydronium H3O plus aqueous plus nitrate ion NO3 minus. So this is the preferred way of writing reactions like this for many, many people. In my opinion, there's nothing wrong with writing H plus in aqueous solution. And so as far as I'm concerned, the first way of writing this chemical equation is perfectly fine. In my opinion, it's understood that when we say H plus aqueous, we mean hydrogen ions that are in water, and because they're in water, they're attached to water molecules. And so as far as I'm concerned, it's not necessary to write out that water explicitly. And in fact, there's something to be gained in clarity by writing this reaction in the first form. The first form of this chemical reaction emphasizes that the hydrogen nitrate molecules, the HNO3, are splitting up in water to form ions. And this is a fact which is somewhat obscured in the second form of the chemical reaction. And for me, the whole point of writing down chemical equations like this is clarity. And so I think that there's nothing wrong with the first version of this chemical equation. And in fact, depending on what it is that you want to emphasize, it can actually be the desirable way to write this chemical equation. But you should realize that if you go on to take more chemistry classes in the future, you may well encounter people who will insist that you always have hydrogen ions attaching to something, usually water. Okay, so coming back to our story, we were talking about acids and bases, and there are a couple of different definitions of the term base in chemistry, but one definition, and the one that's relevant to us right now, is that a base is a substance that forms hydroxide ions when it's dissolved in water. And probably the most famous example of a chemical base is sodium hydroxide, which is also known as lye. Sodium hydroxide, when it's dissolved in water, forms sodium ions and hydroxide ions. And sodium hydroxide is an example of a strong base, meaning that when it's dissolved in water, all of it breaks up into sodium ions and hydroxide ions. Now, sodium hydroxide is an example of a compound that's already ionic to start with, and so we've got an ionic compound that's dissolving in water to form aqueous ions, and that's a typical pattern for strong bases. Strong bases tend to be ionic compounds that contain the hydroxide ion, and so when they dissolve in water, they completely separate and you get a lot of hydroxide ions in solution. Now, an example of a different kind of base is the ammonia molecule. Ammonia has the formula NH3, and when it dissolves in water, the ammonia can pick up H plus from the water, forming ammonium ion, and in the process, it turns the water into hydroxide ion. And so ammonia can act as a base, not because it contains hydroxide ions, but because it results in the formation of hydroxide ions when it's dissolved in water. And ammonia is a weak base, which is to say that when it's dissolved in water, not all of it will react in this way. And so some of the ammonia will pick up an H plus from water with the result of hydroxide ion being formed, but not all of it. And just like we did with weak acids, we can emphasize this fact by writing the reaction arrow going both directions. All right. Now, one important type of chemical reaction between acids and bases occurs when you mix an acid with a base. And when you do this, they neutralize one another to form a chemical called a salt and water. So for instance, if we mix the strong acid HCl with the strong base, NaOH. HCl, we know when that's in water, will break up to form hydrogen ions and chloride ions. Sodium hydroxide, when it's dissolved in water, breaks up to form sodium ions and hydroxide ions. And if you look at all of these ions, if these are all being formed together in water, then the hydrogen ions can encounter the hydroxide ions. And if those two ions meet, they can recombine to form water. H plus OH minus gives H2O. And so that's exactly what happens when these solutions are mixed. You form water, and then the other ions, the sodium ion and the chloride ion, they just stay dissolved in the water. And so the products here are sodium chloride and liquid water. And it's worth reminding ourselves that when we write something like NaCl aqueous, anytime we have an ionic compound that's aqueous, that's dissolved in water, it's important to remember that those ions really are separated. And so this represents sodium ions in water along with chloride ions in water. All right, and that's it for this video.